Today, we are going to look under the hood of the world's most popular search engine to understand the massive scale and clever engineering that powers Google Search. We will explore the hardware, the processing models, and the math that make it all work. Welcome, everyone. Today, we're diving into the underlying technology that powers Google, exploring how it handles massive amounts of data. This presentation was put together by Sudhanva Gurumurthi, and it covers the core systems that make modern web search possible. To understand why Google's infrastructure is so massive, we have to look at the scale of the World Wide Web. Way back in 2008, Google had already indexed over 1 trillion unique web pages, and billions more are created every single day to serve over 1 billion global users. Handling this scale requires 3 main pillars. First, Google uses vast data centers, where a single query runs on up to 1,000 machines. Second, they use MapReduce to process this massive library of pages. Finally, the PageRank algorithm determines which of those pages actually match your search. Let's start with the physical hardware. Data centers are massive, specialized buildings designed to house thousands of individual servers. These facilities, like Google's site in Oregon, provide the raw computing power and cooling required to keep the search engine running constantly. Google distributes this immense computing power globally across 36 distinct data centers. As you look at the global map, you'll notice a heavy concentration of these facilities in North America and Europe, which helps reduce latency by keeping servers physically closer to users. Why does Google need so many computers? Searching 1 trillion web pages for millions of users is like finding a needle in a haystack in less than a second. A simple single-loop program would take far too long. So Google harnesses thousands of computers running in parallel to get the job done instantly. To manage all these parallel computers, Google developed MapReduce. This programming framework, adapted from functional concepts in Lisp, makes it easy for developers to write programs that automatically split and distribute tasks across thousands of physical servers. In Lisp, the map function applies an operator to every item in a list, like squaring a set of numbers. The reduce function then takes those results and combines them, like adding them up to get a single sum. Google took these simple ideas and applied them at massive scale. Google's version of MapReduce uses key value pairs. The map function runs on every item in a dataset and outputs temporary keys and values. Then, the reduce function gathers all the values sharing a specific key and combines them into a final result. Let's look at a practical example, like counting words across millions of web pages. First, the map function scans a web page and emits the word itself along with a count of 1. Next, the reduce function takes that word, sums up all those individual ones, and outputs the final count. This visualization shows how that word count actually flows through the system. We start with simple phrases like "see Bob throw" and "see Spot run." The map phase breaks them into individual pairs, and the reduce phase aggregates them, revealing that the word "see" appears twice. Behind the scenes, a master node coordinates this entire process across several worker nodes. The master splits the input data into chunks and assigns them to workers for mapping. After the workers exchange their intermediate results, the master distributes the reduce tasks to assemble the final output. So, what happens when you actually type a query? Your request goes to a web server, which forwards it to index servers to locate matching pages. From there, document servers retrieve the page details and snippets, compiling the final results for you in a fraction of a second. Getting the results is only half the battle. The real challenge is ranking them. Google must balance relevance, meaning how well a page matches your terms, with importance, which measures the page's overall value. While early search engines used manual directories or simple keyword matches, Google focused on popularity. This focus on popularity led Larry Page and Sergey Brin to develop PageRank. The core idea behind their algorithm is to measure a web page's authority by looking at the structure of the hyperlinks pointing to it, treating each link as a vote of confidence. To simulate how people browse, PageRank uses the 90-10 rule. This model assumes a web surfer clicks a link on their current page 90% of the time and types in a completely random web address the other 10% of the time. It is a simple but highly effective model. Mathematically, PageRank represents the probability that a random surfer will land on a given page. Crucially, links coming from highly important pages, like a major news site, carry much more weight than links from obscure blogs. A page gets a high rank if its incoming links are highly ranked. Let's look at a basic example with just 4 web pages. We start by assuming that the total rank is divided equally among them. In this scenario, pages A, B, C, and D each start with a baseline PageRank value of 0.25. Now, if pages B, C, and D all contain a link pointing to page A, they each pass their entire rank over. This means we add their individual values together, giving page A a combined PageRank of 0.75. If pages have multiple outgoing links, they divide their vote. For example, if B links to 2 pages, it passes half its value to each. If D links to 3 pages, it divides its value by 3. We calculate the target page's rank by summing these fractioned incoming votes. This brings us to the formal PageRank formula. The rank of any page, U, is calculated by taking each page V that links to U, dividing its rank by its total number of outgoing links, and adding those values together. If you want to dive deeper into these technologies, these classic papers are excellent resources. You can read the original Google prototype paper by Larry Page and Sergey Brin, or explore the MapReduce systems paper published by Jeffrey Dean and Sanjay Gemawat. By combining massive parallel hardware with elegant algorithms like MapReduce and PageRank, Google turned a chaotic, expanding web into an organized, searchable library. Understanding these core technologies shows us how modern distributed systems continue to shape our digital lives.